So I was in the gas station this morning filling up, and some thoughtful individual carefully placed these on the ground, knowing that a statistician was going to come by and say, hey, that's a great example for my class. I'm going to grab these things. So it's a couple daily 4 tickets given to me by some anonymous individual. What's the chance that somebody could win there? So let's think. You've got 4 numbers to pick. And this guy did this twice because he had a bunch of tickets there. Looks like he picked 1204 twice. He was really confident that that was going to come up. What's the chance that somebody could win? Now for this game, you've got to take and pick 4 one-digit numbers in a row. So let's take a look at this, and we're going to start figuring out how to count. Now I know you guys think you know how to count. You learned that, before you left grade school. That's great. But we're going to really learn to count. We're going to learn to count in big chunks, mega chunks. So one thing that we're going to look at is something called the multiplication rule. For a sequence of events, the first which can occur in n1 ways, the second occur in n2 ways, third in n3, etc., then the number of possible outcomes is this product. Well, that makes sense. And let's apply that to our particular daily 4 example. So the daily 4 from the Michigan Lottery. We got 1, 2, 3, 4. Four little numbers we had to pick. How many choices do we have for the first number? 10. There's 10 choices for the first number. How many choices for the second number? And there's 10 again. And the third number? And the fourth number. So overall, we've got 10,000 different choices. Yay. So let's play around with this a little bit by way of review. What's the probability of winning? 1 in 10,000. Let's look at the odds against winning. So let's play around with odds just for a moment. Now that 10,000, I can split that up into the one way you win. How many ways are there that you can lose? I'll give you a hint. The rest of yeah, there you go. 9,999. So this is the number of ways to win. And this is the number of ways to lose. So if I ask you for the odds against winning, that would be, well, what would those be? It's going to be something of the form A to B. What would those odds against winning be? Yep, 9,999 to 1. Those are the odds against winning. The odds for winning would be 1 versus 9,999. Now, let's take a look at what the lottery actually pays you if you win. And it looks like you would win $5,000. So, technically, if they were paying you in accordance with the odds, you should win just under $10,000. So, okay, they're keeping a little bit, but don't worry. That money goes to your state's education fund. So that's a good thing. All right, yay. Yay. Let's move on. So, let's see. Across the back, I've got 1, 2, 3, 4, 5, 6. I'm counting. I'm not sure I want to count you as being the back. All right, but we got 6 people across the back. How many ways can I arrange those 6 people? If I wanted to mix you up and put you in different orders, how many ways could I do that? Well, let's take a look here. And we're going to introduce something called the factorial. So if I have 6 choices for the first one, that leaves me with 5 choices for the next one, and then 4, and then 3, and then 2, and then finally 1. Now, mathematically, we'll write that like this. That's your 6 factorial. If this was an English class, what would that be? 6! Yeah, exactly. Yeah. Oz, I appreciate you not spoiling my fun there.
I did.
Yeah, you're biting your teeth. You're like, I know what's coming. He does that all the time. I do. So 6 factorial. Now, I'm not really interested in you taking out your calculator and go 6 times 5 times 4 all the way down. So let's figure out how to do that, first of all, on your calculator and then with Google Sheets. So if you got one or the other, make sure you have at least one of them out. I'll do on your calculator first. So we've got a 6. Type in the 6. Then go to the math key and then over to the left. Well, at least I go to the left there to go to probability. And the 4th option down is your factorial. And bam, there you go. 6 factorial, 720. So, all right, pretty cool. If you're in Google Sheets, maybe you already copied the link over for today's section 5.1. If you're in section 5.1, just click this little plus button down here to add a new sheet so we can put in some calculations down here. What do all our Google Sheets commands start with? Equals. So let's type in an equals and let's sound it out. Equals, well, let's see, F-A-C-T. Oh, look, it's got us for us. So factorial and then do a 6. And bam, there's your 720. Pretty cool, pretty painless. I'm not interested in making you do that kind of stuff by hand. Factorial is an interesting and useful number. It comes up a lot. It grows big surprisingly fast. So right now the Detroit Tigers are going to be teeing off, trying to win the first playoff berth in years. Suppose that for the playing of the national anthem, you line up all 9 starters plus the manager from home plate to first. There would be 10 factorial different ways you could arrange all those people. Now, before we calculate it, any guesses as to how big this is? 6 factorial was 720. How big do you think 10 factorial is going to be? Anyone want to guess? All right, no takers? How many? Yeah, it's surprisingly big. Factorials grow really big, really fast. And 10 factorial is going to be over 3 million. So, wow, that's pretty amazing that it grows so big, so fast. So, 3,628,800. Wow. Wow, that's a lot of different ways you can arrange those. You could arrange those 10 people one way every day for almost 10,000 years and never have to repeat the orders. So it's a big number. Let's take a look at one of the homework problems then. So that would be example B. We'll go back and cover example A in just a moment, but let's take a quick look at example B. A moving company has a truck filled for deliveries to 9 different sites. If the order of deliveries is randomly selected, what's the probability that it is the best route? Well, I guess the first thing we have to do is figure out how many routes are possible. How many routes would be possible if you have to make 9 stops? I think there'd be a little bit more than 9. Your multiples of 9 would take you a while to get up there. What would I do to calculate that? 9 factorial. So 9 factorial is how many routes there are. Of all those routes, how many of them are the best? The absolute best, in whatever sense that they're defining best. Thank you, Nate. 1. There's one of them that's the best over the 9 factorial, which is what, 362,880? It's just 10 factorial divided by that, divided by 10. So, and we just did 10 factorial. Okay. So, all right, not bad. And this idea that there's one of them that's the best, you're going to see that a couple times today, so kind of keep that in mind. Keep it in mind for your homework as well, because it's going to come up there. Let's just back up a little bit and work on example A. We're going to do example A a couple ways. I crossed out repeating is okay. We're going to do it with repeating and not repeating, so we'll do it both ways. So a password for a website is required to be 5 characters long. If the first character must be a letter and the last 4 are digits, how many passcodes are possible? Okay, so let's see, example A. In the first case, we'll do with repeating. Second case, without repeating. With repeating. Without repeating. So we've got 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. So the first one has to be a letter. How many choices do I have there? Ignoring upper and lower case, just dealing with the letter. 26. The next 4 are numbers. What's that give me for the next one? 10. 10. 10. So a 26 followed by 1, 2, 3, 4 zeros is 260,000. That's with repeating. Let's move over and try it without repeating. Without repeating, well, the first choice is 26 for a number of letters, and we have 10 numbers. But what do I have over here for my third digit? Or third? Yep, 9, 8, and 7. Okay, well, let's see how that affects our probability then. And let's see, let me just do that here. So 26 times 10 is going to be 260 times 9 times 8 times 7. So 131,440. 131,040. Which way feels more secure? Which way do you think would be better if you were worried about the security of your passwords? Yeah, with repeating. Yeah, you've got almost twice as many different possible codes, so if somebody's trying some kind of search just by guessing, then they're definitely going to have to do a lot more work here than over here. All right, looking good on those. Let's talk about a little bit more in terms of our counting rules. So for our counting rules, let's go back and look at this thing. We looked at, yeah, question?
Yeah. So if this is a single digit, why would it turn 7?
Because you have to count the 0.
Oh, right. Okay,
Yep.
thank you.
Yep.
Yeah. Oh, I get it now.
Yeah.
That's what I got.
Yes. So 0 through 9 would be the 10 digits.
Okay.
Yeah. I appreciate you helping me make that clear. We're going to have to go through a couple more rules here. So the first rule is for permutations. So the permutations, if you were to take, say, 5 students out of this class, and I'm not sure how many people are here at the moment, let's say it's 25. So soon enough, you're going to get some information about what's called the Michigan Cup from me. And the Michigan Cup is a program that we have with Lawrence Tech, and they take 5 students and you work with a professor, they pay you some money, you get to do research, it's a summer program, look out for it, there's going to be an informational meeting in a couple weeks, and so they ask me to promote it, and I do, but suppose they ask me, well, Jeff, send us 5 candidates and rank them in order. So that's the big thing about permutations, is that they represent how many ways you can take so many objects from a bigger group when order matters. So if we have 25 people here and I choose 5 of them that I want to rank from highest to lowest, then how many options do I have? Well, that would be 25 P5. Now the formula for that is this over here. If you were to put it in, it would be 25 factorial over 25 minus 5 would be 20. 25 factorial over 20 factorial. Those are big numbers. It's a lot to calculate. So let's use some technology for this. On your graphing calculator, type in the 25 first. So type in the 25, bless you. Hit the math key, go over to the probability menu, and you see it there as the second option. 25 P5 should be a pretty big number. So wow, that is a big number. So 637,000, or no, 6,375,600. 375, 600. That's a lot. Now the key thing here is that the order matters. So that's going to be the difference between permutations and the other thing that we do, which is combinations. So combinations is a very similar calculation. I'm sure if you look at the formulas, except here the order does not matter. So if they just said send us 5 students, they don't care, if I rank them or not. They're just 5 students. It doesn't matter if you get picked first or last to be in that group. You're still in that group. Order doesn't matter. So if they just said send me 5 students, then it'd be this calculation, 25C5. And that's going to be a much smaller number. So where we're going to find that, let me show you on the calculator, and then I'll show you on the Google Sheets as well. I'll show you both of those on Google Sheets. So I'll type in the 25 and then hit the math key. Go back over to probability. The third option down gives you your combinations. So, wow, a lot less combinations. There's 53,130 different groups of size 5 that I could choose if we had 25 people in this classroom. Okay, it's a lot less. What if I wanted to do that in Google Sheets? Well, one thing you can do in Google Sheets is just start typing in something and see if it works. Like the first one, I might want to type in perm. And you see it there, number of permutations from a number of objects. All right, well, just hit the tab key, and you're going to type in 25, comma 5. And that should give you the number of permutations. That is, number of ways I could choose 5 people from a group of 25 when the order matters. So, order matters. What if order doesn't matter? Well, then I want combinations. What should I do to try and figure out combinations? Yeah, COM, and there it is, combin. And again, the same thing, 25, comma 5, bam. If you ever get lost, it's like, oh, I don't know, you can Google it. Google is pretty good about telling you how to work with Google Sheets. Yes?
Do we have to memorize these for the exam?
No. On an exam, I will give you any commands that you need, the syntax of those commands. So generally speaking, I'll put that right on your test, a list of the commands that I think that you might need.
Okay.
So like I said, this course is not about learning Google Sheets. It's about learning the statistics. So I don't have any problem just giving you those kinds of commands. All right. But the good thing for you is that not only do you not have to remember the commands, you don't have to remember the actual notation. You don't have to calculate this by hand. You could. It's just a royal pain. And I don't want to spend your time making you do that? Thanks for the question. Let's keep rolling. So the big thing you're going to have to work on is deciding, does the order matter or does the order not matter? That's going to be a big thing. Let's move down to example C here. A clinical test on humans of a new drug is normally done in 3 phases. Phase 1 is conducted with a relatively small number of healthy volunteers. For example, a phase 1 test of a specific drug involved only 6 subjects. Assume we want to treat 6 healthy humans with this new drug, and we have 8 suitable volunteers. Question A. If the subjects are treated in sequence so that the trial is discontinued if anyone displays adverse effects, how many different sequential arrangements are possible if the 6 are selected from the 8 available? There's one word in here that's really important. Did anyone pick up on it? What's the important word?
Sequential?
Sequential? Bridget, do you agree?
Yeah, I was gonna say the sequence.
Yep. Well done, ladies. Thank you. All right. Sequence. So is that saying the order matters or the order doesn't matter? Order matters, yeah. It's in this sequence, so the order matters. If I was in this trial, I'd want to be last. Let the other 5 go first. You know, try and weed out if there's any bad effects. So if the order matters, is that a permutation or a combination? Permutation. Good. The order matters here. So what you should be calculating would be 8p6. And I think there's a lot, a lot of different possibilities here with that 8p6. So let's do that one here. Equals permute 8 comma 6. Wait, let me take a guess at it first.
You already know it.
No, 20,160.
Oh, yeah, you make that calculator.
Yeah.
That's kind of weird. Great.
Nah, it's not.
Big flex.
All right, 20,160. Not so bad. How about the one below that, though? Does anything change here when I look at part B? If 6 subjects are selected from the 8 available and the 6 are selected are all treated at the same time, how many different groups are possible? So the question you have to ask yourself in all of these is, does the order matter?
No, because they're all treated the same.
They're all in the same group. Doesn't matter if you're selected for that group first or last. So you're just in the group. So Jackson, if it doesn't matter if you're, selected first or last, what should I do to calculate the number of groups like this that are possible? Perfect. Combinations. 8C6 should be 28. You guys able to get 8 or 28 on your tech, whatever you're using? All right. Let's follow it up with a probability problem. If 6 subjects are randomly selected and treated at the same time, what's the probability of selecting the 6 oldest subjects?
Can we ask the answer?
Yeah, go ahead. Go ahead, Oz.
Would it be 1 in 28? Because we just calculated this 28 very well.
All right. What do you think? 1 in 28? Well,
It said that
there's
1
28 groups, right? 28 groups of size 6. How many of those groups are the oldest group? There's only one oldest, right? So that would be 1 in 28. Well done, Oz. Thank you. Let's move down to the Mega Millions. This one's kind of nice because it combines a couple things, a couple different things we have to look at. As of this writing, the Mega Millions lottery is run in 44 states. Winning the jackpot requires that you select the correct 5 numbers from 1 to 70. Now, a point of clarification for those of you who don't play the Mega Millions, which kind of includes me most of the time. You don't have to match the numbers in the order that they're drawn. You just have to match the numbers. Doesn't matter what order they're drawn. So you gotta match the 5 numbers drawn from 1 to 70, and in a separate drawing, you've got the numbers 1 through 25. And you're going to draw a single one from that 1 through 25. So let's see if we can't calculate the number of possible winning combinations there are for the Mega Millions. So we'll do this in 2 parts, kind of like I have things highlighted here. So this is part A. What am I going to do to calculate that first one, that first part?
So, all I know is it's gonna be choose, but I don't know which way the numbers go.
Okay. Savannah, do you agree? Is it going to be a choose? Is it going to be a combination, or is it going to be a permutation? Permutation? Does order matter? So if order doesn't matter, which one is it? Is it permutation or combination? Combination. So you've got 70 numbers to choose from, and you're going to choose 5. And then for each of those choices, then you've got to choose a single number from that 25, right? If you're choosing one number from this 25, how many choices do you have? 25. So it's this times this, should be a whopper of a number. So I'll do that one on Google Sheets. Equals combin 70, 5. And let's just do it all at once. Let's see. Maybe I won't. So there's your 70, choose 5, and I'll type equals and click this times 25. So wow, 302,575,350. 302, 575, 350. Is everyone able to get that number off whatever tech you're using? Joy? Okay, all right. I wasn't sure I was, all right.
I'm so sorry. This calculator app I'm using, it gives me ads. If I use it for free, I'm very sorry.
Okay.
Figuring it out.
All right. But it said I'm perfect, so I'm okay with that. All right. Let's, maybe it was wishful hearing or whatever. Now, we haven't quite finished answering the question though. So it asks for the probability of winning the jackpot. I'm assuming it's with 1 ticket. What's that probability then? Probability of winning. What would that probability be?
Is it 1 over 302 million?
Yeah, it's 1 over that big number. 1 over 302,575,350. Wow. So for part B, how does the result compare to the probability of being struck by lightning in a year, which the National Weather Service estimates to be 1 over 960,000? Yeah, yeah. You're way more likely to get struck by lightning than to get struck by lotto. Yeah, getting struck by the Mega Millions would be rare indeed. So let's just circle. Let's just circle. This is more likely. Let's move on down to C and work on another probability or another version of this. How does this probability compare to the probability for the old Mega Millions games, which involved the selection of 5 different numbers from 1 to 75. So let's do that here. 5 different numbers from 1 to 75. And in a separate drawing, a single number between 1 and 15. So there. And separate drawing, single number between 1 and 15. Alex, what do you think I should put here? What should go first?
It should be 75, C5.
75, C5, good. Times what? Ian, by the window? Oh, Gil? Sure, Gil. Times 15. Perfect, thank you, sir. I'll do this one on the graphing calculator. Let's clear out a bunch of this junk. I like to type in the 75 first. You don't necessarily have to, but it works out easier, especially if you don't have a up-to-date calculator. So 75, choose 5. It's going to be a big number. And then after you calculate that, hit the times key and times by 15. So, wow. 258,890,850 equals 258, 890, 9 or 850.
Put it all in one? Will it work? Or is it
Yes, it will. It will. I just out of curiosity sometimes split it up because I like to see how big that first chunk is. But yeah, in answer to your question, let me go back up here, grab that one, and if I just hit times 15, yeah, it knows what to do. So good question. Thank you. You should be able to get this number either way. So compared to what we had originally, if you take 302,575,350 and divide it by, I don't know, this number here, I think it's about 17% more numbers than what it used to be. So tougher to win. But is that better or is that worse? I guess it depends on your point of view. It's harder to win, but what happens is that the jackpot tends to build up bigger and bigger and bigger. And when you get those big jackpots, there's a lot of excitement around that. When it's like $500 million, I think about late last year or earlier this year was close to $1 billion. It's like 900 million or something like that. Yes, sir.
How much of it gets taxed if you win?
All of it, all of it gets taxed. Now, how much gets taken away? I don't know. I guess it depends on, your tax bracket. But now there's, I would imagine it's more than that. I would, yeah. So there's a lot of websites that'll tell you about strategies and don't bet numbers that have come up recently. What do you think about the idea that you shouldn't bet a number that's come up recently?
Doesn't matter.
It's garbage. It's total trash. These are independent events. It has happened in the history of lotteries that a number has come up twice, 2 weeks in a row. It wasn't here in the United States, but it was overseas someplace. If you wanted to follow a strategy that would help you win maybe a little bit more, if you pick numbers that avoid birthdays and things that are common that people pick, you should have more random picks. You're not more likely to win. You're just more likely not to have to share it when you do win. That's what makes that strategy a little bit better. But there's really no good strategy that you can employ in winning these games. The odds are just pretty astronomical.
I feel like if you sit down and you do the numbers and you finally play, you will win. And when you do,
I'll remember Oz. Oz
don't
gave me the
remember
inspiration.
Think of me, find me, and
Find me and set me up for life.
like,
All right.
10,000
Let's keep rolling.
I'll be happy with that, man.
Let's see. let's move over to example E, corporate officers. The self-driving unicycle company was recently successfully funded via Kickstarter and must now appoint a president, chief executive officer, chief operating officer, chief financial officer, chief human resources officer. It must also appoint a strategic planning committee with 5 different members. There are 15 qualified candidates, and officers can also serve on the committee. So let's keep track of things here. You've got president, a CEO, a CFO, a COO, 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 and CHO. How many different ways can the 5 officers be appointed? Well, the big question you got to ask yourself, and this is going to be the thing that I'm going to be testing you on, is does order matter? No?
Well, in this one, it does, right? So
I don't
it'd
know.
be-
You tell me. Does order matter?
Would it be permutation? Does the
Let's-
order count? Yeah.
Well, let's see. If we put Oz here, and then Bridget,
So it'd be CO. Oh, wow.
CFO, Sam, Edmund, and Ryan. Is that the same as maybe Ryan, Sam, Bridget? Let's see, I have to put Edmund here, and then Oz here. Are these the same?
No.
And one of them Oz is president, one of them Oz is not. So does the order matter here?
Yeah.
Yeah. Because in one case, in this case Oz is president, in this case Oz is COO. So those are different positions. So the order that you put these in does matter. And if the order matters, is that a permutation or a combination? Permutation. Good. Permutation order matters. So it's going to be 15P5, which should be a rather healthy number. Are you guys good calculating these things? All right.
Okay, wait a minute. Okay, so the fact that it's saying that, they need 5 more members.
Well, let's not worry about that right now. Let's worry about putting these 5 people into place first. We got to put these 5 people into place in these different positions, and the order matters because in one case you're president, in another case you're not. So the order does matter, and if that's the case, then it's a permutation. Let's not worry about the committee just yet.
Where does it indicate that it's permutation? Where do you get that from?
You have to understand that, where I put these names makes a difference, so that the order matters. No, it's not necessarily an exact order, but the way I arrange these names here and the way I arrange these names here means different things entirely. Because in one case somebody's president, in the other case somebody else is president. So the order does make a difference. Whereas, well, let's just look at this one. You seem a little skeptical still. Is President Matilda the same thing as being COO Matilda?
No, but where
No.
in the thing did it tell you there are permutations? Because I know you can point it out.
It doesn't tell you permutations. You have to realize that, if you're picking the first one as president and the second one as CEO and then CFO, COO, CHO, the order matters because whoever's picked first, that's going to be the president. Whoever's picked second, that's going to be your COO, etc. So if I switch those, that means something different entirely. So the order matters. What was 15 choose 5 or P5 anyways? 360, 360.
Yeah, that was kind of cool.
Yeah, it is kind of cool. That makes it easy to calculate the next one. So the next one, we're back to 15 qualified candidates because they can serve on both. They can serve as both an officer and on this committee. Doesn't matter. So we still have 15 qualified candidates. This time it's just picking 5 people that are on a committee. So does the order matter? No. You look a little skeptical. Does the order matter?
No, I know the second order doesn't matter, but I was just still trying to understand, where we got.
You know, so the order does matter. I mean, let's think of it.
I understand that part. I'm talking about, the 15 qualified candidates, so because they can also serve as officers, that would be, it would
Yeah.
go to the equation for
So-
them as well.
We're back to a pool of 15. It's not like we took these 5 people out and said, okay, you can't look at those for our next pool. They can serve on both, you know, a position on the board and on this committee. So that's why we're back here. All right, thank you. What's the probability of randomly selecting the committee members and getting the 5 youngest qualified candidates? Patty? We would use a combination because we're talking about the committee members, yeah. So what would be the, what's that? Yeah, want the probability of getting the youngest ones. Not 1 in 15.
But if it's 5 over 3,003.
How many committees could be the youngest one? The youngest committee?
One.
Just one. There's just one youngest committee.
But the question asks for getting the 5 youngest.
Well, the 5 youngest form one committee.
There's only one group of 5 that can be made up of.
Yeah, so it's one group of 5 forming that youngest committee. So 1 out of 3,003. All right.
You know what,
Yes, go ahead.
that one actually hit me too, I'm confused. So, you're not getting the 5 youngest candidates.
The 5 youngest candidates form one possible committee. Because remember, your committee is a group of 5. So, where is it? You have a committee, planning committee with 5 different members.
Got it.
So one committee has 5 different members. So those 5 youngest people could form one possible committee. And there's 3,003 possible committees for the whole problem. So that's where you get your probability of getting the 5 youngest ones there.
Okay, thank you.
You're welcome. All right, so we've looked at several different ways to count things here so far. We looked at the multiplication rule, in which you have several different things that can happen in various ways. You multiply those together, that would give you how many possible ways they can all come in. Factorial, how many different ways you can arrange n objects. So that's your n factorial. And then you got permutations and combinations. You're dealing with permutations and combinations when you're taking so many out of so many that are there, but you're not taking all of them. If you're taking all of them, you're probably going to be using a factorial rule. But if you're just taking some of them, you're not going to be using factorial rule. By the way, amuse yourself with this calculation. Calculate 0 factorial. 0 factorial. Calculate it on whatever tech you've got. It's 1. Now, in this class, I can just kind of give you a glib explanation, like there's only one way you can arrange 0 objects. if you were to take my Calc 2 class, I could actually prove where this comes from. But short of that, you're just going to have to take me at our word, or at least the technology that you're using, take that at its word. So from all those things, let's move on to example F. When 9 basketball players are about to have a free throw competition, they often draw names out of a hat and randomly select in the order in which they shoot. What's the probability that they shoot free throws in alphabetical order? Assume each player has a different name. Okay. So we got to figure out how many ways that they can shoot baskets in alphabetical order. So, shoot in order. I'll help you out with the numerator part. Of all the ways that they can shoot in order, or in some order, how many of them would constitute alphabetical? One. There's only one way to shoot in alphabetical order, assuming that all these people have different names. Your job in the denominator is to figure out, well, what is it that goes in the denominator? How many different ways can these people shoot? Which one of the things we have there are you going to choose? There's a couple ways you can think of this, but give that some thought for a second. What's this one look like? Maybe lean over to a neighbor. See what you agree. See if you agree or disagree. What are you thinking? All right. Did we develop a consensus or did we diverge in our opinions? Let's eliminate some possibilities here. Does the order here matter? Then it can't be combinations, right? So the order matters. Now, I wouldn't necessarily choose permutations. Why? Because we're not choosing some of these and excluding the other ones. Permutations formula, generally speaking, we're saying, all right, well, we're choosing to do 5 out of the 12 of these or something like that. We're not doing that. You're using all of them. And if you're using all of them, you're just saying, well, how many different ways can I arrange these 9 people? Okay, so that would be a 9 factorial. So 1 over 9 factorial, 1 over 362,000, what, 880? There you go. Now, if you wanted to force it with permutations, here's something kind of interesting. You can actually do it with permutations. Nicholas, is that where you're heading?
Yeah.
What permutation would you do? 9p9. Let's see why that works. If you look at the formula, it'd be 9 factorial over 9 minus 9 factorial, which is 9 factorial over what? Over 0 factorial, which is 1. So basically it's 9 factorial over 1 or 9 factorial, which gives you the same thing, although I think I'd be less happy to see permutations than I would just the factorial. I mean, that's really what this amounts to. Now, it's not wrong, but I think I'd be happier to see factorial there.
So you heard me over here stressing on both of them, and you think they like agree or disagree?
I'll let you think about it.
Why you do
Nicholas came up with it too, though. So he was stressing the same way. Good job on you both for getting that. So you could do it either way, although I generally think of it, unless you're taking some of these out of play, you know, if you're using all of them, I tend to go with factorial. You can do it with permutations in this case. Let's take a look at example G. With a short time remaining in the day, an Amazon driver has time to make deliveries at 4 locations amongst 9 stops. How many different routes are possible? So think on that one for a moment. Short time remaining in the day. Amazon driver has time to make 4 deliveries amongst 9 stops. How many different routes are possible? So what's the big question you have to decide for yourself?
Which will we use?
Perfect. Say it again.
It's either what rule are we using, or does order matter?
Yeah, which amounts to the same thing. Does order matter?
Yeah.
Yes. Now, if you're not convinced that order matters, let me ask you this. If you're up in Flint, would you take and go to Detroit, then Auburn Hills, and then Royal Oak?
No.
That wouldn't make sense, right? So the order definitely matters here. You would choose an order that would make sense, you know, probably here to here to here. All right? That would make sense. So order matters. So if order matters, what am I going to use for my calculation? Permutations, 9p4, right?
Yeah.
All right. 9p4. How many? 3,024. All right, not bad. Permutations grow a lot faster than combinations. Yes, sir.
Does it matter if you put the 4, like if you put 4p9?
Kind of, because you can't do 4p9. This is how many possible and how many you're choosing. So you can't choose, you know, or I mean, how many possible, how many you're choosing. You can't choose 9 from 4. So I kind of be unhappy. And if you turn those around in like Google Sheets or something like that, you'd get an error. So let's take a quick look here. So it equals permute. If I did 4 comma 9, it doesn't like that. So equals permute 9 comma 4, 4 there, and there, that one works. So it is going to be a little bit fussy about that. Yeah, appreciate the question. Are you getting comfortable with these? All right.
Are you gonna do 32? I mean,
H, sure. Let's do one last one here. Mendel conducted some of his famous experiments with peas that were either smooth yellow plants or wrinkly green plants. If 4 peas are randomly selected from a batch consisting of 4 smooth yellow plants and 4 wrinkly green plants, find the probability that the 4 selected peas are of the same type. This one's a little tricky. First of all, how many choices do we have?
2. Because you gotta add them together, right?
In our denominator, probability of all 4 are the same type. So let's work on our denominator first. How many peas do we have altogether? 8. And how many are we going to take out?
1.
Does the order that you take those out matter?
No. Because it said randomly.
Well, you're taking them out at random, but you're just looking to see which 4 you take out, right?
But when
Do you have to?
pull one out, that removes the same one from the back. So if you
Right.
pull out a yellow, your chances of getting a yellow go down because there's more greens than yellow in there now.
Well, we're not looking at that just yet. What we're looking at is how many ways are there that you can take out a group of 4. So that's the first step in the denominators. How many groups of 4 are there? So groups of 4, is that a permutation or a combination?
Combination.
Order doesn't matter if you're in the group, but it's a combination. So it's there. Now, in the numerator, to be successful, all 4 have to be the same type, right? How many ways are there to get all 4 of them the same type? How many different groups represent all 4 of the same type? Lizzie? 2. You can either have all yellow or all green. Those are the only 2 winning combinations from that. So it's 2 over 8 choose 4. I don't know what 8 choose 4 is, so somebody help me out there. 70? So 2 over 70. I don't care if you put it in lowest terms or not. In this case, it's 1 over 35. That's great. But if you wrote 2 over 70, I'd be really, really happy. Okay. And I think the last one is kind of a duplicate. So are we good on example H here?
Yeah.
All right. Let's put this one in the books. Good luck with this.